networks.
Thank you. Okay, so let's start my final lecture. And yeah, we were yesterday talking about synchronization in networks. And here is what we did yesterday, okay? The first thing we did is to generalize the Kuramoto model, which, you know, it's an all-to-all model, so it's a mean field character, okay, a mean field behavior, into the networked, in a networked system, okay? So we introduced the so-called adjacency matrix that enter into the sum, and somehow filters who are the ones, who are the nodes in which you make the interaction, okay? So it's the neighborhood of each of the oscillators. Then, after introducing the Kuramoto model in complex networks, we move on and we try to derive analytically the expression of the critical coupling. Remember that for the Kuramoto model, the calculation was very clean, so to say, and the explanation was crystal clear, but at variance in networks, we had to do a lot of approximations. And in fact, there are different theories that you can follow, but at the end, what we realize is that after all, these approximations worked very, very well, okay? So it's not 100% correct. There is no theory that fulfills exactly the numerics, but still, qualitatively and even to some degree quantitatively, we can be very satisfied by the performance, even though there are a lot of approximations that we saw yesterday. Then, after studying how structure influences dynamics, in particular the onset of synchronization, we turn the other way around and learn how to use dynamics to infer structure. In particular, we focus on a very specific case in which you have a modular network, but you don't know how many modules you have, for instance. And you put the Kuramoto model, and then you can just analyzing how the system synchronizes, how is the path to synchronization, you can check and say, okay, this network is modular, have different hierarchies of modules, etc., okay? Also, there is another example that Albert introduced in the colloquium, in which you can embed symmetries, okay? If the network have symmetries, okay, you have special nodes that play the same role, then you can also detect these symmetries by inspecting the dynamics. And finally, we are going to couple structure and dynamics. And we can do it in many ways, but we are going to just introduce two main ways, which are adaptive networks, the first one, and the second is explosive synchronization. Well, is the phenomenon that you obtain when you start to play with the structure and dynamics and you couple both, okay? So in an adaptive network, for instance, if you have the Kuramoto model on a network, what happens is that this adjacency matrix is not static anymore, okay? So we have this. We have something that is time varying, okay? But the important thing is that this time variation is not exogenous, okay? Because, okay, it can be due to external things, but in this case, the variation of this matrix has to do with internal states of the system, the variables, here, the angles of each oscillator. And in particular, you can then implement in many ways how these dependence work, okay? For instance, here I want to show you some works that were published already a long time ago, right? In which we propose this kind of equation, okay? Okay, I don't expect you that you detect which is this equation. You recognize this equation from scratch? The variation of something is something, and here is, well, this is the replicator equation, okay? You know the replicator equation? Replicator equation in population biology, okay, tells how, for instance, different traits in a species change because of the evolutionary pressure, okay? So what you have is some kind of fitness. Think here, what we assume here is that you are a node I, okay, and then you have a collection of interactions. Obviously, Ij is one interaction, but J varies across your networks, and these interactions compete with each other, compete for your attention, okay? So that what the constraint is that the sum of all the interactions that arrives to you has to be constant, okay? They can vary in time, but if they start zooming this quantity, they have to remain zooming this quantity for all the time. This does not depend on time, okay? This is what we call homeostasis. You change things, but there are some other things here, the sum of the interactions, that remain constant, okay? This is a homeostatic principle. And the way to implement a variation of the weight of the links so that this quantity, the sum of the weights of the links remain constant for all the time is a replicator equation, because in a replicator equation, what you have is how the fraction of different species, evolve in time. But the sum of the fractions of different species have to remain equal to 1 always, okay? What's the principle that tells you who or which interaction will grow and which interaction will decrease? Okay, then we have, sorry, this is the homeostatic principle. Sorry, this is something that I add just today. So imagine that at some time t, you have this. This is all the interactions pointing to I at some time, and then there is some change due to this equation, and you have another picture in a subsequent time, which is this one, in which the sum of the weights here is equal to the sum of the weights of these arrows here, okay? And this is the homeostatic principle. So let's say, why this decrease the weight and why this increase the weight, for instance, okay? This is encoded in these quantities that we can call the payoff or the fitness of the link. The fitness of the link is given by the degree of synchronization between you and this neighbor. The more synchronized you are with this neighbor, the more you want to connect to this neighbor. It's like Hegelian learning, okay? And this is what we call homophily, okay? You want to stay with those neighbors that are closer to your state, okay? So here, the reason why this and this changed to this and this is because before, we have a color which was very similar to this one, and this was very different. And now what happened is that this color has turned very, very close to this one, and this very different, okay? So the synchronization here has decreased, so the link has decreased, and the synchronization between these two has increased, so that the link has increased, okay? And these are the two principles that governs the evolution of the system. Any question about this? Okay? Okay, so these are the two principles, homeostasis and homophily, that drives the system interaction. Sorry, I want to come back here and tell you that this quantity is, again, the same correlator we used yesterday in order to unveil which was the functional network or for the synchronization process. Remember that yesterday we have a network with some structure, and what we did is to measure how two nodes were synchronized. And according to this degree of local synchronization, we assign a weight to the functional link, okay? So this is a measure, and you can obviously use many, many measures, many different measures, in order to account for the internal degree of internal synchronization of two connected nodes, okay? And here we have a parameter, which is t, okay, which is the time that you are inspecting the internal synchronization between nodes, and together with lambda will be the relevant parameters of our model, okay? So this is what we get when we inspect the global synchronization, remember the Kuramoto order parameter, and the degree of local synchronization, which is different, okay? You can be globally not synchronized, but locally very well synchronized, okay? Imagine, for instance, a lattice, okay? A chain in which there is a large degree of local synchronization between adjacent nodes, but the degree of synchronization follows a gradient. So after all, the global synchronization is very low, but the degree of local synchronization is very high. And this is what happened here, because, for instance, if you look at some time, okay, here and here, you see that by increasing lambda, so we increase lambda from here to here and also from here to here, you reach an area, this one, in which global synchronization is still very low, while local synchronization is very, very high. Okay? Remarkably high. There is a big difference between these two quantities, okay? And this is something that, okay, here depends on t, but for some large enough t, you don't have any kind of change. Last day, I put this picture because last day someone tell us, how I know that t is large enough? okay, in this plot is clear. If you have 80 and 80, you see that is invariant, okay? So T large enough here in this system is T larger than 80, okay? So you do the numerics, you do the experiment, and then you decide how much time you have to wait in order to measure local synchronization between these two within systems, in order that system is the results are invariant on the choice of the window, okay? Any question? Yes? Sorry? Ah, sorry, no, sorry. Well, you have to average, but typically here we are using a very narrow degree G omega, like a Lorentzian, for instance, okay? So in order that they are not the same, okay? Because obviously if they are the same, sorry, this is a mistake, a big mistake, that this is omega I, so these frequencies are different, because otherwise they will synchronize, okay? Well, this is a very good question. We start with a not fully connected, but random regular graph. This means that all the nodes have the very same degree, but the connections are randomly chosen. And the mean degree, again, is much smaller than the size of the network. So it's a network, okay? It's very far from being an all-to-all coupling, okay? But it's regular. We didn't want, from the very beginning, to introduce any heterogeneity in the system. We want, in fact, that the heterogeneity emerge from the dynamics, and we will see that this is what happened, okay? Okay, the important thing here is this, okay? We find a regime in which the system globally is not synchronized, but locally is very well synchronized. What happened here? And this is an example of what happens in this, for a fixed time, equal to 100, in this point. This is this one is this, and this point is this. And you see what happened. The degree, the global synchronization is fluctuating, but you see the range of fluctuation from 0 to 1. So a lot of fluctuations. It's not constant anymore. Typically, in the Kuramoto model, in networks or in the normal Kuramoto model, you reach a stable, obviously with some fluctuations, but a stable degree of global synchronization, and you always take the average synchronization as the measure which is relevant to the dynamics. Yes? This is a very good question. Let me know. I have to check, but yes, it's not orders of magnitude larger, I guess. It's of the same. It's not the same, but you have to check the external cases of the degree of the frequency distribution. Okay. Okay. Any other question? Yes. Yes. And now we are going to see why this is somehow periodic, okay? But you see, okay, this is also, they have a very large fluctuation, non-periodic. This is aperiodic, believe me. And this is, yes, and this, you know why? Because the network has split into modules, naturally. The network has suppressed. Remember that we are starting from a random regular graph. Everything is connected homogeneously, and the network has selected some connections so that modularity show up, okay? And in fact, if you make a same diagram, but looking for the modularity of the network, what you find is that the larger modularity is just in this area and in this area, okay? So you have networks in which you have very low global synchronization, very large local synchronization, high modularity. And what happened here about the heterogeneity of the links? Okay, let's take another time this range of values in around t equal 100, and we have, sorry, we have this. This is the structure of the network. You see high modularity, and the important thing is that for these cases in which the network is not split into modules, because there are still connections between modules, if you plot the distribution of the weights of the links, remember that the strength is constant, so we are allowed to change the weight of the links, what you find is a power law. Okay, so you have heterogeneity in the weight distribution, you have modularity, you have low global synchronization, and you have very high local synchronization. Okay? This is an example in which you can reach, I mean, Albert was telling, and also myself, Kuramoto model is an oversimplification. But you have no soul if you cannot see the brain here. Okay? Obviously, it's the Kuramoto model, obviously. But you have features from scratch, from very simple principles. I'm not claiming this is a model of the brain. But you are recovering features that you observe in this kind of systems with a very simple formulation and two simple rules that, okay, I mean, homophily and homeostatic plasticity is something that we know apply in the brain. Yes? They stabilize. Yes. Very good question. Especially in this area in which you find, okay, obviously, these kind of networks are here, just always in between to the emergence of local synchronization and when still global synchronization is really, really small, okay? Yeah. Sorry? Okay, this is because you have finite size, okay? But if you are with larger networks, then you have, exactly. Okay, this was just an example, okay? But you see what you can do with a very simple model and with very simple rules, and obviously this is not a model of the brain, but you can understand, and maybe it's helpful for you in order to go to, obviously, more complicated models, in order to understand how these kind of features could emerge in a different setting, which is much more complicated, okay? Okay, let's go to the other phase of coupling that I want to address today, which is explosive synchronization, okay? The story starts with this paper, well, not to start with this paper, okay? But this paper inspired a lot of works, in particular our work in our lab. It was done by Raisa da Sousas and Lioptas and Spencer, and what they did is to change the typical percolation process to construct a network. In the typical percolation process, you start from a set of nodes, and then you add a link, okay? So that when you have added enough links, a giant component emerges, and you have the percolation transitions. For a very small fraction of links added, you have isolated components with a size which is orders of magnitude less than the number of nodes, and finally you have this transition. And typically the transition, the normal transition, for instance, is this one, the black one, okay? So what they did is, okay, let's change it, and at each time step, instead of adding one link, we will think about adding two links. But we have to decide which of these two links we are going to add into the system, okay? And for instance, here you have, this is the network, you have components that are very small, and then you, at this time step, you check if you add this link or this other link, okay? And what you do is to make the product of the size of this node, of this cluster, and the product of this cluster, and compare with the result of making the product of the size of this cluster and the size of this cluster. And decide to take the smallest value of these two, okay? So for instance, here you have 1, 2, 3, 4, 5, 6, 7, so 14. 1, 2, 3, 4, 1, 2, 3, 4, 16. So you place this one, okay? And that's all. And you continue the process. So at each time step, you add one link, as in the original process, but now what you have done is to compare which link you have to put in order to minimize this local rule, which the important thing is it's a local rule. And if you do this, what happens is that you get an explosion. The transition is no longer smooth, but you have an abrupt. It's not first order, by the way. It has been checked by a lot of numerical and theoretical means. But the important thing is that it's really abrupt, okay? So you add links, you add links, you add links, you add links, and at some point, without any previous signal, you have no warning, there is a sudden emerge of a giant component, okay? And the problem of this kind of system is that you don't have any previous signals. You have not early warnings, okay? Well, it can be good, it can be bad, depending on the application of the system, okay? So, okay, we saw this paper and say, explosive synchronization, this was called explosive percolation. I say, okay, let's try to analyze what Raisa and collaborators did. What they do is to connect the dynamical rules, which is the process of addition, with the structure of the network that you have at this moment, okay? And the idea is, and this is something that we knew because we already did some work on jamming and similar things happen in the jamming transition. The thing is that when you try, typically, okay, when you try to delay the transition, as a byproduct, it's very usual that you also obtain an abrupt jump, okay? For instance, in jamming, instead of having packets navigating the system going through the shortest path from the origin to the destination, I say, okay, now the packets will know about the congestion state of the system and can make some kind of longer trips, but in these trips, the path they find is less jammed, so they are not waiting a lot of time, so they reach the destination at the end earlier, okay? If you do this, it's nice because the jamming point delays a lot, but the problem is that you have an abrupt jamming onset. So without, again, any previous signal, any early warning, you are in a state that in this case is dangerous, okay? So we analyze what we have learned before, and we have learned that, for instance, if you compare how scale-free networks, heterogeneous networks, and how homogeneous networks goes to the synchronization as the coupling between nodes increases, those networks that are heterogeneous anticipate the onset, favor the onset. And what we learn, and this is something that we saw yesterday, is that those hubs, those nodes that are largely connected, are the responsible of this anticipation of the onset, okay? Because they start to form a synchronized cluster from the very beginning, and by an agglomerative process, they start to incorporate more and more nodes so that they construct a synchronization cluster very, very early, compared to the percolation-like process that happens in Erdős ranging network, in which you don't have any highly connected node, and different clusters, very small, appears, and you have to wait until this point, which is here, in which this cluster collapses and make a larger cluster, okay? So this is what we learn. So the recipe is the following. We want to delay synchronization. We know that the responsibles of this anticipated onset are the hubs. Let's go for the hubs, okay? Let's try to harm the hubs so that they cannot make this cluster, synchronization cluster anymore, okay? So this is the rationale. Okay, hubs are the responsible of synchronization because they integrate a lot of signals, so they know very early which is the synchronization frequency they have to reach, and then they reach this synchronization frequency very early, and then they pass this information to many nodes, so it's a feedback between these two things. So we will destroy this ability by assigning them a frequency which is very large, and very large is the degree. So we close the loop. The large degree of the hubs is the responsible for their ability to make a synchronized cluster, but if they have a natural frequency which is very large compared to the mean, which in this case the mean is also the connectivity, the average connectivity, then I destroy this ability, okay? So this is the recipe. As a byproduct, as I say, the mean frequency now is also the mean connectivity, and also the frequency distribution is now the degree distribution, okay? This is the byproduct of making this, okay? This is what is known now as the correlation degree frequency setup for explosive synchronization, okay? Okay, let's see what happened. If you do this in a homogeneous graph, you don't see nothing. Why? Because this recipe is targeted to systems in which you have hubs. Otherwise, I mean, there is no effect of the recipe. But what happens if you do this in a scale-free network, in a heterogeneous network? Bah. You see? The typical transition now, and this is a real first-order transition because you have also hysteresis, you have B-stability. It means that if you start from here, you don't see synchronization, you continue increasing the coupling, you don't see synchronization, and suddenly you go to the synchronized state. But when you want to come back, you come back in another branch, the backward branch, in which you stay in the synchronized state longer, or for less coupling, and then finally you come back to this state. And this area, in these values of the coupling, what you find is two stable states, because in the middle there is an unstable one, but you don't see it, obviously, because this is a subcritical bifurcation. And then you have a B-stable system, which is very important because you have switches. Okay? If you put your system here, then you can have switches, biological switches, for instance, in order to jump from one state to the other. Yes? This one? It's the unique, the first time someone asked me about this. Okay. No, no, because you don't have areas with full synchronization and other areas without synchronization. Yeah, it's that in between. Yeah. Yeah, we check this because we have the microscopic, all of these things, we check not only with the global synchronization parameter, but also with the local one, so we can measure cluster of synchronization, and when we detect something which is something synchronized, like in a chimera state, then we can detect it, but in this case, no. Okay? Any other question? No? Okay, let's go. So another way of watching the transition is just monitoring as a function of the coupling the effective frequency, which are not the natural frequencies, is the effective frequency, the real frequency each node have. And you see here that initially the effective frequency are the natural frequencies, and that's why this discrete, degree 3, degree 4, degree 5, degree 6, okay, because the natural frequencies and the degree initially are the same. And you see in an Erdos-Renyi network, what you happen is a sequential addition to the synchronized cluster of the nodes. But if you do this in a scale-free network with the recipe, what you find is a sudden, I mean, almost all the nodes remained ignorant of the coupling until you reach the coupling, the coupling strength that makes you collapse into the synchronized state, okay? And this was an abrupt transition, okay? Okay, there were works much before in which in the original Kuramoto model, no networks, that's why it's different, because here I need the network in order to implement this. It's making an interplay of the structure, here the degree, with the dynamics, the natural frequencies. But much before, the same Kuramoto noticed that by varying the frequency distribution, you can also obtain this kind of jumps, okay? There were works by also Kuramoto, Patho, for instance, in which you have this kind of jumps. But this has to do with G omega. The question is, maybe what's happening here is that because G omega now is the degree distribution, and the degree distribution is a power law, and this is an exotic frequency distribution, maybe this is the responsible of this jump, okay? And the answer is no. Because what we do is, okay, now we assign the frequency and the degree to the nodes, and then reshuffle the values of the frequency, okay? We restart. So now the degree distribution is still a power law, but there is no correlation frequency with degree because we have reassigned the frequency. Okay? We have the same set of frequencies following a power law distribution. In fact, you see different power law distribution for the degree frequency, and you see that you don't observe the explosive anymore. So you need really the couple structure and dynamics in order to see this kind of thing. Is the only, well, you can make theory. I will go very fast because here we apply it in order to gain insight to a very simple model. And this is also a typical toy network that we use a lot in order to gain insight about what's happening in heterogeneous network. Okay, this is not a scale-free graph, of course, because if you look at the degree distribution of this graph, you will have a bimodal distribution around 1, because all of these nodes have degree 1, and around the k, the degree of the central node, which is very high compared to the others. But here you have a system, a minimal system in which you have heterogeneity, because you have one single node, which a degree which is much larger than the average, okay? So we take this system as a toy model and try to analytically derive how is the synchronization transition in order to verify finally that this is actually a first order phase transition. So now what we have is this star graph. You have k leaves, so the number of leaves is k. The leaves have a different frequency, have all the same frequency, okay? And this frequency is very different from the one of the half. So that the average frequency is k times the frequency of the leaves plus the frequency of the half divided by k plus 1. That's all, okay? If you do this, you have two sets of two different equations. One equation for the half, in which you have, obviously, the sum across all the leaves, the k leaves, and one which are equivalent for all the leaves, okay, in which you only have the interaction with the halves. Be aware that here the leaves are not interacting with each other because they only interact with the half, okay? So this is very important. Okay, so you can proceed in this system as we have proceeded around these days, okay? So you transform this equation into an effective equation. This is for the half, in which we have changed the summatory by this term, in which we have the typical Kuramoto order. Then look for the steady state solution, and you find that this is the condition that the angle of the half, of the sinus of the angle of the half, must satisfy in order to get transition, okay? Then with this condition, you also analyze the leaves, and again, by expanding this sinus of the difference, you can obtain the steady state condition by putting here 0, and this is the steady state condition that already tells you which is the critical value of the synchronization, because this quantity has to be larger than 0. This is larger than 0 by definition, and this is the condition that tells you when synchronization will happen, okay? Because lambda has to be larger than this difference in order to have this steady state condition available, okay? And then with the former half condition and then for the leaves, you can compute the value of the Kuramoto parameter that we have learned that at the end is the sum of the cosines of each node in the steady state, obviously. So what we do is the average. So this is the number of nodes we have. This is the cosine for the leaves. So you have to multiply it by k, and this is the cosine for the half. Obviously, this is the square root of 1 minus the sinus to the square of the face of the half. Okay, so you can have the expression of the Kuramoto order parameter at the transition point. Okay, and what we check is that in our case, if we set, for instance, the omega for the leaves equal to 1 and the omega for the half equal to the connectivity k, so that this is the average frequency, we have that this is the critical coupling, and more importantly, that at the critical coupling, you find this value for the Kuramoto order parameter, and this value is really large. It's not small, okay? And you can verify it with numerics and see that, yes, this is the value that you find. To check which is this other critical onset, not this one, which is the one we have derived, this one, you have to do other theories that we are not going to enter it. But the important thing is that this critical point remains barely the same. Look at the dependence with k. But this point depends a lot on k. And you see what happened with this point when you increase k. So the more you increase the number of leaves, the larger is the V-stability region. So if you are interested in constructing devices in which you have V-stability because you want to have switches, then you need to put a lot of leaves, okay? So this opened the door. Okay, this is what happened to scale-free networks. This is for different values of gamma, blah, blah. Okay, the important thing, this opened the door to experiment, okay? So we have a star system, which is very simple, and we have a recipe that seemingly works. So it's not the only recipe, okay? There are other possible setups. This is the one we have checked. But there is also others, like this one, like this one, like this one. In this one, for instance, what you incorporate, the feedback between dynamics and structure, is that the coupling now changed into from a constant for all the nodes to something that depends on the natural frequency of the nodes and also the connectivity of the node. Okay, so for large for hubs, this coupling decreases because this is very large. And for those nodes which are very far from the synchronization frequency, so it's in the tails of the frequency distribution, the coupling is increased. And if you do this, you also obtain explosive synchronization. There are adaptive also scenarios in which, again, the coupling is not constant anymore for all the nodes, but depends on the nodes, and in this case, depend on the local synchronization of the neighborhoods. Remember that this is not the synchronization of the node with the neighbors, but it's the synchronization of the networks among themselves, okay? So if you do this, you also get an explosive transition. Or this one in which you have a network and you have to decide which is the frequency you assign to the node, and you have to fulfill this condition, which is very hard to fulfill, by the way. The condition is that if you are neighbors, the difference between the frequency of you and your neighbors should be larger than gamma, okay? And if gamma is large enough, then you have also explosive transition. In any case, in all these cases, you couple dynamics with a structure. And in all the cases, the idea is to suppress the emergence of a synchronization component. As I said, many times, when you try to delay an onset, as a byproduct, what you get is an explosive transition. And here is the example in synchronization. Okay, experiments. We have this star network. We have a simple recipe, but the bad news is that the Kuramoto model is something that you cannot implement in the lab, okay? It's, again, a very simple model, a toy model, allows you to get a lot of insights, and this is gonna be, and now you're gonna see how by gaining knowledge from the Kuramoto model, we can transfer this knowledge into real setups, okay? The one we did with the group of Madrid by Inmaculada Leiva, Irene Sendiña, Javi Buldu, and colleagues, and also with the group of Lagos de Moreno, Ricardo Sevilla, which we have now a student of Ricardo here, is to transfer it into electronic devices, okay, and in particular transfer it into Rosler circuits, okay? Okay, this is the typical Rosler circuit that you know, linear system, non-linearity here. We have studied it very well, but when you go to the lab, you have Rosler that are quite different or a little bit different from the typical model. And what you have is, we implement a coupling in the first variable. This is the coupling. Here is the nonlinearity, which in this case is a piecewise nonlinearity, okay? And these alphas, as usual in the Rosler systems, are the frequency, okay? The frequency of the Rosler oscillators. And what we did is to assign a frequency, this is something that Ricardo colleagues could make, is to assign a frequency that depended on the connectivity of the circuit. And in particular, with these that are controlled by digital potentiometers, we could adjust the coupling, and now we can check, and yes, if you do this assignation, the frequency proportional to the degree, you obtain an explosive synchronization. And the good thing is that you obtain this in a regime in which there is chaos. So this is synchronization, not of a simple signal of phase oscillator, but synchronization of chaos, okay? So chaotic synchronized signals. There are other, following this recipe, there are other examples for instance, here in mercury beating systems, or in nonlinear nonlinear optics, for instance, in which you also obtain experimentally, following this Kuramoto recipe, an explosive transition, so you can have these switches that you are interested in, okay? So the important thing here, Kuramoto is not real, we know. It's very simple, okay? But you can get a lot of insights and then transfer into real systems, okay? Like these ones. And finally, okay, you transfer it into the lab, but you observe it in real world. Okay, I'm not sure about it, okay? I'm not an experimentalist. But there are some works, like this one, in which they say that the only plausible mechanisms behind, for instance, the transitions between conscious and unconscious states in anesthesia, or, for instance, the frequency detection of the cochlea, etc., the only plausible or the more plausible mechanism is explosive synchronization, okay? I like a lot the last, and let me just mention this work, because they put a lot of effort in, sorry, well, no? in trying to build which was the mechanisms, the the particular mechanism of explosive synchronization behind what's happening in the hypersensitivity of fibromyalgia patients. So they made a lot of experiments, recordings, EEG, they measure the frequency of each of the nodes, then also they construct a network, which obviously is a functional network, but they assume it's a structural network. So here you have frequency, here you have the network, so you have degree, and finally you construct the network, and you see that the correlation, degree and frequency, which is what we impose artificially, explains the intensity of chronic pain. So it seems that the abrupt change between the non-pain and pain state in these patients is related to a kind of correlations of this. See, I don't have to say anything about this. It's just a work in which they observe it experimentally. Okay, any question? Sorry, louder, please. Kuramoto model, you cannot plug it. Because it's not, experimentally, you cannot make a Kuramoto model. But why? What's the point of coupling this? If you have explosive synchronization only with Rosler oscillators, No, the idea is this one. You cannot connect them. Okay, you can connect Kuramoto model with the Stewart-Landau model. You can connect the Kuramoto model with the Kuramoto-Sakauchi, with many models. In fact, the Kuramoto model at the end is an approximation of many models in which the amplitude of the oscillation is not constant. Rosler oscillators are far away from Kuramoto, that you cannot connect. The idea is that the knowledge that you have gained, when you transfer it into mercury-beating systems of Rosler system or lasers, which are very, very far apart, well, lasers not so far apart, but from Kuramoto, it works. Okay. No, you cannot make a path from the Rosler oscillator to Kuramoto. And, well, I don't know it, but I'm quite sure that you cannot, but for many reasons. Okay. Mm-hmm. Mm-hmm. No, because in springs es linear, pero es linear. Pues Winfrey oscillators. Winfrey. Porque son linears. Es decir, que, en el régimen no lineal. Bueno, sí, pero no sé. No sé si es tan controlable. No, pero sí. What is true is that there are systems that are closer than the Rosler to the Kuramoto system, to the Kuramoto model. For instance, Josephson junctions are very close to the Kuramoto model, okay? And you can make it with Josephson junctions. In fact, I know that people try to make it with ANSI explosive synchronization. I don't know if they succeed or not, because this is something that I stopped studying. But in this case, a Josephson junction under certain conditions is really, really close to the Kuramoto model. But with springs, I don't know. Okay. Theoretically, yes. Okay. So we have 45 minutes. And we start the last lesson. Don't worry, this last lesson was intentionally shorter, okay? And the idea of this last lesson is that we have to change the focus, okay? This is the synchronization transition for the Kuramoto model or for Rosler system, whatever. We have a critical coupling. This is the decoherent state. This is the onset of synchronization. And we have focused on this onset. In fact, we have learned how to derive it in the Kuramoto model. We have learned how to derive it in the Kuramoto model in complex networks. We have learned how the way the path to synchronization close to the onset tells you about what's the structure of your system if you don't know it. And we have played with the onset. No? For instance, we have just played by changing this onset from being continuous to being abrupt. Okay? And now we focus on this part, in the fully synchronized state. And the question is the fully synchronized state stable, or it can be unstable by changing some parameters? What happens if we are in this area, okay? And to do this, okay, well, this is a very important question, for instance, in power grids. In power grids, we need that all the systems or the subsystems that compose the power grid work in a synchronized state. Because if they become unsynchronized, everything is sorry, a blackout appears. Sorry. So, in order to address the question, we can do it, I mean, by brute force. Brute force means, okay, imagine that we have a nodes, like this one is the power grid in Europe. Each node is a m-dimensional dynamical system by their own. For instance, in Rosler systems, we have 3 dimensions, m equal to m. In Kuramoto model, we have 1. ICTP-SAIFR neurons, 2 variables, okay? M is the dimensionality, which typically is low dimensionality of the dynamical system. And we have n nodes. So we have n times m coupled system, okay? Coupled variables, n times m differential equations, for instance. And the solution to the stability of, let's say, a fixed point is just to compute the Jacobian, okay? So you take the F, which is the equations governing the dynamics of each node, the collection of dynamics of the nodes. You compute the derivative of this F with respect all the variables, the n times m variables that you have in the system, and you have this matrix, okay, in which each element is the derivative of these functions with respect to the variables evaluated at the fixed point, okay? And that's all. And what you have to check is that all the eigenvalues of this Jacobian matrix are negative, or the real part of the eigenvalues are negative. And if you do this, then you are sure that your system is stable. And if you do this, and you can inspect which is the dependence of this matrix with the parameters, you can also, in principle, unveil which are the conditions that remain, that makes the system staying in the stable state, and which are the critical conditions that destabilize it, okay? This is in principle brute force. The problem is that n can be very large. Imagine a collection of neurons in a culture, 1,000 neurons is ICTP, so 2,000 by 2,000, and this is a very simple system, or 2 millions by 2 millions, okay? So this is in principle what you can do, but even you can have a computer, but again, you don't have an insight, okay? Even if you can do it, it's difficult to have insights. Okay, can we do something better? Okay, can we do something better in order to disentangle, and this is the important thing, disentangle the large scale of the network with the low dimension of the dynamics? So let's try to separate the contribution of the architecture of the network and the contribution of the low-dimensional dynamics, okay? And this is what we are going to do. So let's start from the very, very beginning. Obviously, we will make some assumptions, no approximation, assumptions, okay? And these assumptions, let me say, are valid in most of the situations. So they are not very, very strong assumptions. So we have a node. This is a system. In this system is described by these variables, 1, 2, m. So we have xi1, xi2, xim. And if this system is isolated, we have this m-dimensional dynamical system, okay? So we have, for each I, a collection of m equations, each one for each variable, and this is the form of the equations, okay? That's all. And for another node, we assume that, again, it has the same number of variables with the same meaning, okay? So if this is a Rosler, this is also a Rosler. If this is a Kuramoto, this is also a Kuramoto. If this is a ICTP, this is also ICTP, okay? Again, 1, 2, m variables for this node J. And the thing is that J interacts with I. And the function of the interaction of J to I is this one, okay? And also, obviously, I interacts with J. The function driving the interaction is this Jij. And obviously, I is also influenced not only by J, but from all nodes, from other nodes, okay? This is a network, remember, okay? Not a number of nodes of the comparable with the size of the system, but a number of nodes, okay? So we have to add a coupling term here that accounts for this interaction, this interaction, this interaction, and this interaction. Okay, this one. Again, we sum across all the nodes, so J run from 1 to n. This is the filter of the adjacency matrix. And finally, we have this coupling for each J to I that depends, in principle, of the two states of the system. Okay? Remember the Kuramoto model? This will be the sign of the phase difference. Okay? Obviously, in the Kuramoto model, m is equal to 1. This is the sign of theta j minus theta I. Okay? That's okay. So far, so good. And there's the first assumption is that all the functions that describe the individual dynamics and all the functions that describe the interaction between them are equal. Okay? For instance, in the Kuramoto model, the sign is always the sign. Okay? So all of them have the same functional form. Okay, so this is our equation, and see what happened. At the end, the system is described by these kind of equations. This is for one single node, so for this node we have m equations, one for each component, and we have two functions only, f, which describe the individual dynamics, which is Rm to Rm, and j, that in principle describe the interaction between two nodes. It has two m variables, it has m here and m here, so it goes from R to m to Rm. Okay? Okay. Let's assume we are in a fixed point, and this is another assumption, the second assumption, and this is a symmetric fixed point, okay? Symmetric fixed point. Okay, Jesus, symmetric fixed point is very usual. For instance, the rest state, 0 for all the nodes. If we are interested, for instance, in destabilizing the resting state of a culture of neurons, okay, you have to assume that in principle all the neurons are in the same fixed point, and you want to check how long or what's the coupling, the critical coupling that destabilizes this state, for instance. Or if you are in a synchronized state, by definition, the synchronization means that all the variables are equal for all the nodes. Okay, so this is another assumption, but again, is realistic enough in order to continue and have this class here today in Sao Paulo. Okay, so let's do the linear stability analysis. That means that we assume that there is a perturbation, so that the nodes are perturbed from this state, the synchronized or the fixed point state, with a different perturbation. Look that this is another time a vector with m components, because this is for a node I, and we have to check which is the evolution of this perturbation, if it grows in time or if it downs out and is stable. That's all. Okay, so I put this expression into the main equation. So here I have x star plus the perturbation. Here I have xi plus the x star plus the perturbation for I. Here I have x star plus the perturbation for j. And here, obviously, I have directly the sum of this and this. Obviously, this is 0 because this is a fixed point, so this is 0. So only this term remains. And for this and this, what I do is to perform a Taylor expansion and stay in the first order approximation. So I neglect all the terms of power 2 and higher, okay? And if I do this, I have equations for each of the perturbations of each, no, for each of the components of the perturbations of each node. Remember, I goes from 1 to n, and alpha goes from 1 to m, okay? Okay, so these perturbations have the following evolution. The first term accounting for the evolution is the one accounting for the series expansion, for the Taylor expansion of f, and remaining until first order. So we take the component alpha, because this is the equation for the component alpha of f, and derive by all the components, the m components, 1, 2, 3, blah, 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 m, that are the variables of f. And obviously evaluate these derivatives in the fixed point, okay? Nothing more, nothing else. Then I go to this term, the coupling term, and here I have two variables, so I have this and this, okay? Again, obviously I put ij, the derivative of j with respect to the first, second, and m, but the first variable u, and here the second variable v, 1, 2, and m, and obviously evaluated, all these evaluated in the fixed point. No doubts, right? This is the typical linear stability analysis that you perform in a dynamical system. Okay, so We can compress this form. So instead of having the sum, we put beta going from 1 to m. Okay, so beta goes from 1 to m. We have the perturbation for each of the components. We have here the Jacobian, the components of the Jacobian. Alpha is here, alpha, 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 and beta is 1, 2, 3, m. Okay. Then I do the same for this. Look that there is a sum here over j, but nothing depends here on j, so I can do it this sum, and that's all. And the sum over j of ij is the connectivity of I, okay, because it's the sum of the I row of the adjacency matrix. So after making the sum like here of beta, this is the result of making this sum, and this is just the compression of this summatory. Look that here I have stated that we have the derivative with respect to the first variable because we are deriving with respect to the first variable. And finally, we have this, but in this case, I cannot solve the sum because here depends on j. So I have to put in this way. Okay? Any question? No? Okay. Nice. These are the three components that we have. Still, we have, sorry? Where? In the second term. No. No, because here you have it, but this one. But nothing here depends on j, so I make the sum, and this is ki. Ostras, casi me caigo. Sí, culpa de Gil. Okay, so these are the three terms governing the evolution of the perturbation of the component alpha of node I. Nothing more, nothing less. Okay, we still have a very large system, okay? So let me put a sum, because we have here two sums, j and beta. Here only have one sum. Let me put also a sum j, so it's just a question of putting a delta here, and that's all. It's just to homogenize. And you can now see that this is a matrix. You can put it in a matricial way. So we have a matrix with 4 indexes, ji for the nodes, beta alpha for the components of the dynamical system. So if I know the vector of the perturbations, I trigger this into a matrix, and I have the evolution. If I can run this, okay, I can check what's happening with the perturbation. But again, the problem is that the matrix is very large. Let's explore the structure of this matrix because it's important. So we have a mn times mn matrix, and this matrix is composed by n blocks, 1 to n, 1 to n, okay? And inside each block is m times m submatrix, okay? And that's all. These are the indexes, and because we have this delta here, we know that those in the diagonal have this form, okay? For the diagonal, have this form. Again, you have m times m, so this is for alpha 1, beta 1, alpha 1, beta m, alpha m, beta 1, alpha m, beta m, and the form of these entries are encoded in this part. And for the other part, okay, and it only depends on the individual dynamics because this is the function of the individual dynamics, and this is the derivative, but with respect to the first dynamic. So it's only depend on the dynamical system on the node, and that's why it appears on the diagonal. On the contrary, the other term appears in the off-diagonal part, and look, because we have this filter, not all the blue blocks are activated, only those that correspond to connections, so connections denoted in the adjacency matrix are active. The others are 0, 0, 0, 0, 0, okay? So in principle, you see that we have a diagonal with this structure, and off-diagonal, according to the adjacency matrix, with this structure. So we can be tempted to write this as a tensorial product, okay? The diagonal tensorial, the white matrix, the yellow matrices, plus the adjacency matrix, tensorial, the structure of the blue boxes. Okay? We can do this. Does anyone see a little problem? in order to do this, we need that these matrices are the same, because otherwise we cannot write the tensorial product. And there is a problem here. It depends on I. The case of I that resulted from the sum that you notice, this is a problem. So I cannot write this still. Okay? Okay. Well, what we have still is this matrix, as I said. It's a m times n matrix. You can solve it. You can find the eigenvalues, in fact. And if all the real parts of the m times n eigenvalues are negative, then you know that the system is stable. But again, so far so good, but nothing of interest until now. Okay, let's do another consideration. And let's now consider a special case in which this function is of this form. This means that the interaction does not depend on the state of I, but only depends on the state of the neighbor. For instance, this is not valid for the Kuramoto model, because in the Kuramoto model, you have the difference between your face and the face of the neighbor. But it is the case, for instance, for the Bauman model of opinion. In the Bauman model of opinion, there is an input, which is the opinion of the other, and it's only this variable, okay? This is very general. This is a reactive, in fact, this is called a reactive interaction. And if I have this case, what happened? That this term is 0, because the derivative of j with respect to the variable, with the first variable, because this does not depend on the first variable anymore, is 0. So the problem that we have is no longer there. And I tell you, this is valid for many systems, okay? Okay, so now we can write this, because now, yes, this matrix, which is this, okay, this is the Jacobian of matrix of function f, is the same for all the entries of the diagonal, so I can write it as a tensorial product, and this is great news. Okay, now what we can consider is all the eigenvectors and eigenvalues of matrix A. Obviously, and consider an orthonormal basis of A. Obviously, this basis is also a basis of this matrix, because this is the diagonal matrix. So now I will exploit the fact that I have written this matrix as a tensorial product of the very large dimensional matrices, the identity and the adjacency matrix, which are n times n, and very low dimensional matrices, which are the Jacobian of f and j, okay? So I take the eigenvalues, okay, and I write the perturbation as a function of the eigenvectors of I. Obviously, the derivative of the eigenvectors are related to the derivative of the coefficients, because the eigenvectors are fixed in time, and I put this and this into this equation. One goes here, and one goes there. Let me put this sum here, so I have a full picture. Okay, this is the full picture, and now what happened? This is an eigenvector of this matrix and also of this matrix. So let's activate the sum over j, and then I have here the eigenvector of A, and here a 1, obviously, because this is the identity matrix. So I have this one, okay. Any question until now? Everything clear? Okay. I'm trying to be very, very, very step by step. I cannot do better. So now, because this is an orthonormal basis, I can consider each of the m terms separately, okay? So imagine that this is your perturbation vector, the whole perturbation vector. And this is for node 1, this is for node 2, and this is for node m. And you have the m1 entry here, m1 entry here, m1 entry here. I like these chokes. You have the m equal to entry here, the m equal to entry here, the m equal to entry here, and let's say we have m equal to 3, 3, and 3. So now I'm taking this one, this one, this one, and this one, and construct an n-dimensional vector, one for each node, corresponding to the m component. and here 3, 3, 3, 3, okay? Yes? And this is what we do. For each nu, okay, we have this, this equation that we can collapse. And this equation, the important thing of this equation is that it's an m-dimensional linear equation. Because remember that these are numbers, because this is the Jacobian evaluated at the fixed point. This is the Jacobian evaluated at the fixed point. So this is a linear equation, and it's only m times n. 3 times 3, 2 times 2, if you have an ICTP-SAIFR model. 1 times 1, which is a scalar equation, okay? The thing is that we don't have only one equation. We have n equations, because we have one single equation for each eigenvalue of the adjacency matrix, okay? That's all. Okay, let's focus on one. What you have to do if you have one equation like this and you want to see what is the evolution of the coefficients? You have to check the eigenvalues, the m eigenvalues. And again, if the real part of the m eigenvalues of this matrix are negative, then you say that the system, for this eigenvalue of the Laplacian, the adjacency matrix, for this specific eigenvalue of the adjacency matrix is stable. So, if you solve all the equations for the first eigenvalue, for the second eigenvalue, for the n eigenvalue, and in all the cases you have that the m eigenvalues are negative, then the system is stable. I say, okay, Jesus, but now, yes, you have matrices that are low-dimensional, which in principle, this is okay, because you can put it in MATLAB, and that's all. And you put a 4 for each of the eigenvalues, but it takes time, because now we don't have a system, n, m, and m, but we have an n times m, okay? Still large, but better, okay. Now, the nice idea comes with this paper by Lou Pecora and Lewis Carroll. And the thing is, okay, don't worry. Take this as a parameter. Take this as a parameter. And you have to solve this equation, one shot, okay, as a function of lambda. So what you do is only compute the largest eigenvalue, because you don't care about the rest of the, if the largest eigenvalue is negative, that's all. Compute only the largest eigenvalue for this equation as a function of lambda. Forget that this lambda is an eigenvalue. This is a new parameter. A parameter as the coupling in the Kuramoto model or the activation threshold in the ICTP-SAIFR neuron or whatever. It's a new parameter. And this is an m times m matrix. So you have to calculate this single function, the maximum eigenvalue of this linear system as a function of lambda. And you do it, and you can obtain what is called the master stability function. And this master stability function, for instance, has this shape. So you see, okay, this is a function that only depends on f and j, but does not depend on the structure of the network. In fact, tell me which kind of individuals I have, which is the language they speak, but I don't care who speaks with whom by now. Only tell me this, and I can calculate this. Then, I take the network, I consider the adjacency matrix, I calculate the eigenvalues, and now plug from the maximum to the minimum these eigenvalues here. And if for all the eigenvalues I have that are placed in the negative party, the system is stable. Okay? And we have light. Otherwise, we can have this situation, and then we have, in this case and in this case, that the eigenvalues are positive and the system is unstable. Okay? So I have to compute a function that only depends on the dynamics, remember, the kind of individuals, F, and the language they speak, with the structure, which is who speaks with whom. Okay? So two matrices, adjacency and this one function, and the decoupling is set. Any question? Yes?
Stability is a local stability or a global stability?
Local. This is a linear stability analysis.
Okay, because globally this could be stable
Exactly, this is local, this is local. Okay? Any other question? Okay, let's follow. Let's continue. Let's now consider another case, which is this one, which is also, this is a diffusive coupling. And this is also very often, you find it very often in models. So now we have that our G, our original G, depends on the first variable as well. So we have the problem of the connectivity, remember, and this prevented us from writing the matrix as a tensorial vector, a tensorial product, sorry. So, but now we have the following. It's not a general G of xi and xj. It's a G in which you have an m-dimensional function, j, minus the same m-dimensional functions, but applied to the neighbor. So in this case, what happened is that the derivative of j with respect to the first variable is minus the derivative of this function j with respect to the second variable. So that we can change this and this by dg, well, minus dg, write it here. Ki still remains here, but let me make a trick, which is not an approximation, it's just a trick. Let me call it this yellow and this blue. And now, let me write it as this. And this is a new matrix, which is called Laplacian. Very well. Okay? And now I can continue writing everything. This is the Laplacian as a tensorial product, but now I have here the adjacency matrix. Sorry, the Laplacian matrix, not the adjacency matrix anymore. Okay? This is the F, as in the first case. This is now the J, as in the first case. But here, the thing is that I have the percent. So I am not going to repeat everything, because, again, now you take the eigenvalues and eigenvectors of the Laplacian, decompose everything in terms of these eigenvalues. It's an orthonormal basis. You can separately blah, 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 blah. And finally, you reach to the very same m-dimensional equation in which you are only interested in the maximum eigenvalue of this equation as a function of lambda, and you have to compare with the eigenvalues, but these eigenvalues now are those of the Laplacian. Okay? So if in the master stability function you have to compare with the eigenvalues of the Laplacian or the adjacency, depends on the way the coupling, you have the coupling with the rest of the neighbors, okay? Okay, again, the mission is accomplished. We have decoupled the dynamics from the structure, and we can address if the synchronized state in a given system is stable, okay? Well, this has been for a symmetric fixed point. What happens if I have a synchronization manifold? It's not a fixed point anymore. We have a synchronized solution. It's homogeneous because all the nodes have the very same state at each time, but this state changes in time, okay? If you have this, then the story is the same. But now, the problem is that these matrices are not longer numbers, fixed numbers, because when you evaluate it across the trajectory. So they depend on time. What you do typically in this case, you have the answer there. You don't focus on the maximum eigenvalue, you focus on the maximum Lyapunov exponent of this system. And again, you compute the maximum Lyapunov exponent of this dynamical system, obviously, again, as Pecor and Carroll did, as a function of lambda, and again, you have a function you have to compare with the eigenvalues of either the adjacency matrix if you are in a reactive coupling, or those of the Laplacian matrix if you are in a diffusive coupling. That's all. Okay? Okay, let's put some examples and we will finish with this. This is a Lorentz system, famous Lorentz system. And if you couple the Lorentz system via reactive coupling in the first variable only, this is the shape you have of the master stability function. So you need that if you have a network, so the network is not there anymore. I only say that I have a certain network with a Lorentz system coupled in the first variable. Then I can already compute this. And now I say, okay, don't give me the network. Compute the eigenvalues of the Laplacian. If they all are situated here, the system is stable. And that's all. Because we have decoupled the dynamical system from the structural patterns of the interactions. If we put in the second variable is this way, it's very nice, but again, we have a lot of range for stability, and the nicest picture comes with the coupling with the third variable, because in this case, we have this one. So you have two areas. It's difficult that you can fulfill that some of the eigenvalues are here or some of the eigenvalues are here. But in principle, this is the master stability function, and this is what it tells you. You can go and try to put all of them here. Well, this depends on what you have to do, okay? Rosler, which is the the typical one, also with Lorentz system. This is the real Rosler system, not the experimental one. Again, we have three variables, and if we put the coupling, again, look, this is the diffusive coupling, so we are interested in the Laplacian matrix. Weighted with this K, this is the interaction weight, and this is very important, okay, because at the end, it will be what allows us to tune the stability of a given network. Then we have this kind of master stability function. Okay, this one for the first variable, and this is for an Erdos-Renyi graph, okay? And you see that here we have some eigenvalues of the Laplacian that are outside the safety area, okay? If you do this in a heterogeneous network, you have obviously the very same function because it doesn't depend on the structure, and you have a broad range because the Laplacian have a spectral radius, a larger spectral radius, but still here you have this that prevents you to have a stable system. What you can do is what I anticipated. Look that this lambda can be written as the eigenvalues of the Laplacian times this k. So I can tune the k, tune the coupling, in order to move the eigenvalues towards the right by increasing lambda. And now we can control synchronization. Obviously, take care, because here you have a danger part, okay? So depending on the form of the master stability function and controlling with the coupling between the units, you can adjust and have light or not, okay? Depending on what you want, okay? Okay. So I have 10 minutes more. I could make examples. I have prepared some examples, but I think mission is accomplished, okay? So we have explored these 3 days all this diagram. It's true that we have focused on the Kuramoto model, but I hope convince you that the Kuramoto model, despite its theoretical value, is also valid for gaining insights, okay? And I hope that this last part, the master stabilization, has been understood finally, because I know that many of you have worked with it, but have difficulties in understanding when it is valid, what are the assumptions, etc., etc. I think we have accomplished this. And as I said, this can be used for models that are related to neuronal dynamics, okay? For instance, the Sikevich model or Fitgum-Nagumo. So you can use this more refined model with the master stability function and look for this kind of stability conditions that, for instance, make that your system start to spike from a quiescent state, for instance, no? Which is very important. And that's all for my part. Thank you very much. I need a cachaça, not a coffee.
Thank you very much.
Thank you.
It was very nice and informative. I think there are lots of questions. Or tilt. You have a question.
Do you know if there is any important cases where this approach breaks down? For instance, this works for diffusive coupling or for that reactive coupling. Are there other cases that are known to be important and where this breaks down?
Well, for instance, what I know, higher order networks and multiplex networks, you have different kind of connectivity. For instance, in multiplex networks, you have this reaction, and also you have another contribution, which is with layers, and then you have complicated situation. In all the cases I know that separate from this, the strategy is always the same. Trying to see how much we are far from this situation, and try to consider the limit, that the limit in which the difference is the less. Okay, so. And this is, for instance, what we did in multiplex networks, and in the case, for instance, the two layers. So you have the interaction here, and also the interaction here, which is so is not these fundamental cases. In the cases, the two matrices have a similar set of eigenvectors, or the more similar the set of eigenvectors are, the more closer you are to apply this. So this is the typical strategy, unfortunately. But maybe there are other cases that I don't know, okay? But in my own experience, which is limited for sure, is always try to accommodate to these scenarios.
And also, just to understand, this idea of plotting and maximizing the value of functional lambda, it's very nice if you have that analysis.
Yeah.
That's numerical, it's easier just to check.
Yeah. This is something that, I mean, the price that you have to pay is that you have to have the whole range of eigenvalues in an analytical way. But depending on the form of the function, maybe you say, no, I only need the maximum one. Okay, so it depends a lot also on the shape. And the shape is for free. Well, it's not for free, but I mean, it's very easy to calculate from scratch.
I have a question about this. Before you mentioned a case in which there was a variation of the structure, that is, of the connectivity matrix.
Adaptive case.
Yeah, sorry?
The adaptive case, the homeostatic
yes,
plasticity.
That's the case. That's the case.
Mm-hmm.
So, do you know, is there a study in which you look at something like this last part that you had been showing, and in which they treat the case in which everything changes in time, because all this depends on that your stability, your connectivity matrix will be constant.
Yes. So, I think there are some works for time-varying graphs, and I don't think there are works for adaptive equations like the one I saw, because you have this coupling, but maybe you can do it. But for time-varying graphs, I think there are studies in which you apply, obviously, the maximum, you apply something, the techniques in which you assume that, for instance, you have a series of adjacency matrices, you have a periodic condition, so there are a lot of restrictions there. So still, these kind of works are very initial, because you have to fulfill a lot of closure relationships in order to tackle the problem. But this is a field. I think this is something that we have to tackle, definitely.
Yeah. Okay, thank you.
So I just had a very similar question to Ilda. So because I think in the field, for instance, of learning, there is always this question of you can tune, you can have some dynamics. Like at the end, if you learn, for instance, if you look at the dynamics of motor behavior, you can find these low dimensional structures. And there is the question of what individuals do. You can tune the network to kind of get these dynamics, but you can, or it's you tune the dynamics and then you get this type of
this is, so you can do both. For instance, my experience with neuronal cultures tells me that there are two options. If you have the neuronal culture already grown, okay, then you can add some chemicals in order to inhibit the interaction, or to activate more interaction. In this case, you are playing not with the structure, but with the interaction. And another thing you can do is to start with a little network of neurons that is forming, so it's growing, and manipulate it in order to have a set of eigenvalues that goes according to something. So this is some work that we did with Jordi Soriano a long time ago. Well, no, 3 years ago, no, not so long time ago, actually. And we explored this because with the Isikevich model, for instance, he has the problem of having the culture already grown, and then you can perturbate it, okay? Or you can monitor and kind to manipulate the way it grows from single cells. So it starts making connections, so the spectral radius starts to grow because the connectivity starts to grow, until which point you will have, for instance, that the neuronal activity changes from one state to another. Okay, this is the kind of things that we are trying to explore. I don't know in other setups, but this is what I can say, similar to what you are saying in my own experience.
Thanks.
Thank you. I have a question more about explosive synchronization.
Okay.
Since until now I've never been familiar to the concept, but so maybe it's a question about someone who hasn't had more attention to this phenomena.
Mm-hmm.
But I was going to ask, you showed some biological phenomena linked to neurons and etc. But I was going to ask if you've ever known or ever seen any works investigating explosive synchronization on species, because at least for me it looks like a lot to invasive species on ecosystems, the way they function.
In the ecological setup, I don't know any kind of example. Most of them, as I saw, which is the literature we review in order to know which kind of setups we could apply our studies, is always at the level of cellular systems. So either neurons, but not only neurons, also biological switches that you can control in the lab, etc. But at the level of a species, so in the population ecology, I don't know why. Because synchronization in ecology, well, yesterday I saw an example in which I use synchronization in order to see the structure of an ecological system, but not because in the ecological system there are a synchronization process running. It's just a methodology, okay? I don't know if synchronization is the collective phenomena that you are interested in. What you can do is to try to consider models in which other collective phenomena shows up and try to check if there are similar mechanisms, but in other models that drives you to this B-stable state. This is a very relevant question, okay? But you have to check other kind of models, I guess, another kind of collective phenomena.
Yeah, that's right. Thank you.
Coffee.
Yes, this is exactly what I wanted to say. If not, then thanks to this again.
Thank you.